this lesson, we're going to focus primarily on special nuclear material. What is it? Where does it come from? And how do we get our hands on it? Now, there are other factors that are involved in producing a nuclear weapon, and we're going to talk about those a bit later in the course. Now, there are three categories of material that we need to talk about in the context of special nuclear material. And these are fissile, fissionable, and fertile. So what does fissile mean? Well, fissile simply means that this particular nucleus can sustain a fission chain reaction. And for those of you who have not taken NENG 596, what that means is we can get one nucleus to fission by usually introducing a neutron to it. When it fissions, it produces more than one neutron. Those neutrons then go out to fission other nuclei, who then produce more neutrons, and so on and so forth, so that we exponentially can increase the energy of this chain reaction. Now, when we talk about nuclear weapons in particular, the fissile material that is normally discussed is uranium-235, plutonium-239, and then to a lot lesser degree, uranium-233. However, it should be noted that there are other isotopes, that is nuclei with different numbers of neutrons and protons, that can also sustain a fission chain reaction. And the only other one that's really relevant to this course is neptunium-237. We'll talk a little bit more about what parameters are important when discussing these fissile isotopes. Now, fissionable isotopes are these nuclei that can undergo fission. However, the energy of the neutrons released during their fission events, they're generally not high enough to go on and cause that exponential increase in the number of fissions. So it really can't sustain a nuclear fission chain reaction. Now, fissionable isotopes, pretty much you can find a whole bunch of them from uranium on upwards on the periodic table. One of the most important ones, as far as we're concerned with, is uranium-238, which comprises the bulk of naturally occurring uranium. It's not really super important for this particular discussion, but when we start looking at producing something like plutonium, it then becomes relevant. And the last category we need to look at are fertile isotopes. And these are simply nuclei that we can introduce something like a neutron to, and while they will not fission, and they're not fissile isotopes, by capturing a neutron, they can then be transmuted or transformed into a different nucleus which can sustain a nuclear reaction. Now, some of you are probably wondering, what's the deal with this little symbol with the red strike through it? That's just an old alchemy symbol from way back in the Middle Ages, where it was thought you could do things like turning lead into gold through various chemical reactions. We know that, in fact, that's not true. But what, in effect, we are doing is the modern equivalent of that when talking about fertile isotopes, which are we're taking something like, in the case of uranium-238, it can absorb a neutron and then undergo subsequent radioactive decays and turn into plutonium-239. So we really can change from one element to another, but it's very highly specific, and it's nuclear-based and not chemical-based. I just thought it was a neat little thing to put in there as a callback to what we used to think we could do with different types of elements and materials. So I mentioned that a fissionable isotope, while it can undergo fission under the correct circumstances, it doesn't generally produce neutrons that have a high enough energy to sustain a fission reaction. So what's the justification for this? Where are these neutrons coming from, and how do we determine what energies they're going to have? Well, anytime you fission a heavy isotope, something like uranium or plutonium or neptunium, it produces, basically it splits into two other nuclei, but then it has a random smattering, a distribution of neutrons that are also coming out at the same time. And we characterize the energy of the neutrons that are being produced by something called a Watt spectrum, which is right here. Now, the Watt spectra, I put the formula up here. For anybody who's interested, you will not be expected to know this, but the point I was trying to make with this is that the Watt spectra only changes very slightly depending on what isotope you're talking about, be it uranium-235, uranium-238, and then some of the more exotic ones that you may have heard of, like californium-252, americium-241. All of these different isotopes that can fission produce a very similar energy distribution of the neutrons that come out, and they're described here. Now, what I want to point out is, looking at this energy distribution here, we see that the most likely energy neutrons that are produced are right around 1 MeV. And then we see 2 MeV, about 2.5 MeV is about right here. And then, 4, 6, and so on. Well, for most fissionable nuclei, they require at least 2.5 MeV of neutron energy in order to fission. And if we look here on this distribution, we can see that that's basically from this point all the way to the end, which comprises probably less than 20% of all the neutrons that are being produced. So in essence, we're not going to see enough of those high energy neutrons that are capable of going on and providing the additional fissions that we would need to sustain that chain reaction. So we can take a look at, more specifically, two different types of isotopes. We have a fissile isotope in uranium-235, and then we have a fissionable isotope in uranium-238. So that whole thing I was just talking about with the different energies that are required really comes into focus here. So let's take a look at the graph here on the upper left, which is uranium-238. Now, what's being plotted here are the cross sections, or interaction probabilities. And I have 3 of them listed. One is in blue, and that's the total interaction probability. And that covers a whole bunch of things. That covers capturing neutrons and turning into something else, fissioning by neutrons, capturing neutrons and spitting out other neutrons without fissioning. And that really, the order I just put those in is basically going from highest probability to lowest probability, but they're all combined into that total probability that's reflected by the blue line. Now, the green line is the probability of fission. So if we can go right here at the beginning and we can look, so this is 10 to the 5th. So this is going to be 100,000. Then we have 1, and then so we have 1, and then 100 and 1,000 and 10,000 and so on. And what we can see is that the probability of fission occurring is extremely small when compared to the total interaction probability. And then the other piece that's important to note is this red line, which is the probability of neutron capture. Uranium-238, when it captures a neutron, as I mentioned before, will then subsequently undergo radioactive decay and become plutonium-239. That's the part of uranium-238 that makes it a fertile isotope. The fission makes it a fissionable isotope, but the difference between the capture possibility and the fission possibility is what makes it not a fissile isotope. So we can see that for most of this energy range that we're seeing here on the x-axis, it's way more probable that uranium-238 is going to capture a neutron than it is going to fission by one, all the way until we get right around here to about 2.5 MeV, in which case the probability that it's going to capture decreases rather rapidly, but the probability that it will fission goes up dramatically. So the big takeaway from this is, if it has a capture possibility or probability that's so much higher than fission, then it's not a fissile isotope. However, if we look at uranium-235, we can see that the total cross-section in blue and the fission cross-section in green, all the way up to about 10 to the minus 5 MeV, they're practically the same. The lines are sitting right on top of each other, with capture lagging about an order of magnitude below that. However, when we start going to higher energies, we don't see that flip that we see with uranium-238, where fission becomes more probable and capture becomes less probable. In uranium-235, fission is always more probable, and capture falls off as we go into higher energies. So because it's more likely throughout most of its energy range to fission than it is to capture, we can look at a graph like this and say, okay, that's probably a fissile isotope. So just by looking at the cross-sections or the probabilities that are involved, we can generally distinguish between those different types of special nuclear material: fissile, fissionable, and fertile. Now, uranium-235, again, is not the only isotope. I only put it there because we're going to talk about it first. When, generally speaking, and historically, when we're looking at what types of special nuclear material or what specific isotopes that are commonly used, we have uranium-235 and then we have plutonium-239. We're going to start talking about uranium-235 and we're going to move into plutonium-239 a little bit later in the course. And then there's a third that's not pictured in this particular little diagram, which is uranium-233. And we will also talk about that a bit later. But this is kind of in a nutshell, diagram of how do you get a nuclear weapon. So if you're going for uranium-235 to build your weapon, you start here with mining natural uranium, which is, mostly uranium-238 with a very small percentage. In fact, it's 0.71% of uranium-235. So if you're going to make a weapon out of uranium-235, you need to get naturally occurring uranium, and then you need to separate out the uranium-235 in order to build a sufficient mass of that fissile material to create a weapon. Now, the second is the plutonium route, and specifically it's plutonium-239, and it also starts from mining and processing natural uranium, because we're going to use that uranium-238 to capture neutrons to turn into plutonium-239, rather than trying to extract the uranium-235 that is part of that naturally occurring element. So the first route we're really going to look at is the so-called uranium route. Now, the process of extracting the uranium-235 from the uranium-238 is something called enrichment. Now, once you have that enriched uranium-235 material, you then need to turn it into the core of the weapon, which requires some fabrication. Once you have that done, then you need to do some things like look at high explosives in order to assemble your weapon, your critical mass, which we'll go into in a little bit. You need to have a means of putting it all together so that you have something that detonates when you want it to. And then finally, you need a way to get it to the place where you want to detonate it. So all of these things down here at the bottom is basically what I just talked about. And we'll go into those again a little bit later in the course. But right now, we're going to focus on enriching uranium to something called weapons grade. So you might ask, well, uranium is in the world. Where is it mostly? So I have two different maps here. One is a global map showing basically reasonably obtainable uranium deposits. And then I have a map of the United States showing, for our particular country, where are those deposits located. So if we look at the world, the size of the squares corresponds to the amount of reasonably obtainable uranium resources. We see Australia by far has the largest amount. Then coming in sort of tied for second place, we have Canada, Kazakhstan, and Namibia. Then in third place, we have places like Russia, Niger, Brazil, and South Africa, and then kind of everybody else after that. If you look, the United States doesn't really have all that much, comparatively speaking, to these other countries, reasonably obtainable uranium deposits. But we do have them. And so now we look at the second map as to, all right, well, where is most of this uranium located? So we have two different colors. We have red and we have this pinkish color. And so we have uranium districts, clusters in other areas. That's mostly uranium ore that you can just dig right out of the ground, basically rocks containing uranium. And then we have uranium-bearing phosphate deposits, which are a bit different. And if you're really interested in what the difference of those two things are, please shoot me an email and I'll be happy to explain it a bit further. But in the interest of keeping this video mostly short, we'll just say there are two different types of deposits. Now, if we look at where they're occurring, you can pretty much see that right along this area here, this is kind of where the Rocky Mountains are. And so all along the Rocky Mountains, the Colorado Plateau, New Mexico, Arizona, and then we have some more here in Texas. And then we have our phosphate deposits, also kind of following the Rocky Mountain line, moving up into Wyoming, excuse me, and Idaho over here. That's not Wyoming, that's Montana. But we do have some scattered deposits in the Carolinas, Tennessee, and Florida. Sorry, my geography is not what it should be. Okay, so we're not the biggest producers of uranium. We don't have the largest deposits, not by far. That is definitely Australia. But if you're wondering where that stuff was, you can take a, just refer to this little map, as a handy dandy reference guide. Now, once we dig the uranium out of the ground or we get it from whatever deposits it happens to be occurring in, then what do we do? Well, the stuff that we dig out of the ground, we call it ore. Usually, ore is just, some sort of conglomeration of different types of minerals that contain the specific element or material that we're looking for. In this case, it's U3O8, and we can kind of grade how, the quality of the ore that we're pulling out of the ground in terms of how much uranium does it actually contain. So high-grade ore is kind of what we're interested in, and that's the stuff that's really economically feasible for extraction, which goes to the world map that I just showed you. And it contains somewhere between 1 and 20% of the ore by volume is that uranium oxide compound. Now, I mentioned previously that when we pull uranium out of the ground, it's mostly uranium-238. Only 0.71% of it is uranium-235. Natural uranium, because it's mostly uranium-238, it can't sustain that fission reaction, again, because of the energy considerations. So it's not useful for a nuclear weapon. We have to do something to it in order for it to be useful. What we do use natural uranium for is for a very specific type of reactor, something called a Canadian deuterated natural uranium reactor, or CANDU reactor. And we'll get more into when we talk about reactors as to why that one particular reactor can use natural uranium and nothing else really can. Now, well, you can also use a graphite moderated reactor, but the only way that that's ever really been used is for weapons plutonium production. But again, we'll talk about that in the section on reactors. So once we get the ore out of the ground, we dissolve it with sulfuric acid and process it with ammonium, and we get something that's called yellow cake. And yellow cake is simply processed uranium ore. It's just a shorthand notation for it. It's called yellow cake because although it looks kind of orange in this particular picture, it does have yellow coloration. Fun fact, before the whole uranium being used for power in nuclear weapons, uranium oxide was used as a dye in certain types of ceramics where it would produce this orangey color that you see here. Now, yellow cake is can contain somewhere between 75 and 85% U3O8. It's not 100% U3O8 at this particular point. We can then take that yellow cake and we convert it into something we can use. Now, the most common thing that we use, and it's used for uranium enrichment, is something called uranium hexafluoride, or just hex. Uranium hexafluoride is basically, we take that yellow cake, we heat it up, it gives us UO2, and then we introduce fluorine to it until eventually we end up with UF6. And UF6 is kind of an interesting material, and the reason that it's chosen is that while at room temperature it is a solid, it doesn't require a whole lot of heat to become a gas. And since most of the enrichment methods that we're going to talk about later require a gaseous feed, UF6 is probably the most prevalent form of uranium that's not in the ground. Yellow cake is important because that's usually what's moved around the world before it's processed. And because you really can't do anything with yellow cake until it's processed into something like UF6, there are no international standards that regulate or inhibit trade of this yellow cake material. Now, people that want nuclear weapons, proliferators, they always try to get their hands on yellow cake. The reason is because they're not very smart and they don't know how much effort you need to go from yellow cake to something that you can use in a nuclear weapon. And again, as I mentioned, it's not restricted in trade by any currently existing treaty. Now, once we have our yellow cake and then we start processing it in order to increase the amount of uranium-235 and decrease the amount of uranium-238, we can then put it into these 4 different categorizations. Natural uranium has not been processed in any other way than getting it out of the ground and putting it in some kind of form that will be used. And again, this is approximately 0.71% uranium-235. But there are a couple different areas of the world that produce an ore that is higher than this, all the way up to just under 0.9%. The next category is something called low enriched uranium, which has less than 20% uranium-235. And when I talk about these different percentages, we're talking about by mass. Since you could also say by volume, since they are pretty much equivalent in mass. They differ very slightly. So if I had a 10 kilogram chunk of yellow cake that was at natural uranium, then only 0.7% of that would be uranium-235. Low enriched uranium, about 20% of that would be uranium-235. Then we have something called highly enriched uranium, or high enriched uranium, HEU. And anything above 20% is considered to be highly enriched uranium. So 20% is the dividing line, just something to keep in mind. And then finally, we have another categorization, which is called weapons grade uranium, or WGU. And it's generally it's about 90% and above uranium-235. But that number is a little bit variable depending on sophistication of a weapon design as to, what percentage it could actually use. So there is a possibility that that number could go 90%. You could maybe get away with using 85%, which would still be considered weapons grade. But for most intents and purposes, for discussion, weapons grade is usually 90% and above. So the next topic that we're going to cover is the enrichment of uranium. That is, how do we get more uranium-235 than we do uranium-238? There's several different methods that have been used historically or have been proposed historically as ways to enrich uranium, and we're going to look at all of them and some of the specifics as to how this actually occurs.